Okay, so I'm going to work through two examples here. One's going to be a square root, one's going to be a cube root, and we're going to take an entire radical and then convert it into a mixed radical using two methods here. So the first one's going to be, let's try and use our perfect squares table in order to quickly find the solution to this. And then the other method is going to be breaking into a prime factor tree or breaking into its prime factors and then selecting the values for this. So first of all, let's use our table here. What we want to do is, in order to simplify this, we want to select the largest perfect square that can divide 448 or 448. In this case, what we would say is that that's going to be equal to 64. So if we divide 448 by 64, we're going to be left with 7. And now, how can we rewrite 64? Well, 64 is actually a perfect square. It's actually equal to 8, just from our table there. So we get 8 squared times 7. Now let's separate them in their own radicals. So we have 8 squared times root 7, because anything under the radical we can actually separate if they're being multiplied. And then 8 squared square rooted is just going to give us 8. And then 7 we'll just keep as root 7 because it cannot simplify any more than that. So that's how we would select the largest prime factor or the largest perfect square from our table, and then use that in order to simplify to get our mixed radical solution. Now suppose we wanted to go the other way and take 448 and divide it using into its prime factors and then construct this same thing. Well, let's actually show how the breaking into its prime factors is actually the root of why we're able to do this. If I take 448 and I divide it by 64 just as I did before, and then that's going to give me 7. If I divide this by 8, which will give me 8, then I get 4 and 2 and 4 and 2, and then I finally get 2 and 2 and 2 and 2. So that's breaking it into all its factors until the point that they're all prime numbers or the prime factors of 448. Now what we want to do is, if we're square rooting, that means we have to have two equal groups of the prime factors. I'll repeat that. We need two equal groups of the prime factors. So what that means is one group is going to have to be labeled. If we know we have what looks like 6 2's, if we need two equal groups of the prime factors for it to square, then I'm going to have to highlight 3 2's and 3 2's. Because we have two equal groups of the prime factors available. Then if I do the two equal groups of the prime factors, well, what's 2 cubed? 2 cubed is just equal to 8. So if I'm going to construct this root 448, what I can actually say is this is equal to 8 times 8, because we had the two equal groups of the prime factors and they multiplied to make the 8's, and then times 7. Now I can go square root 8 squared times 7, and then we can follow the same process and just separate them into their own radicals. And finally, what's the square root of 8 squared? That's just 8 root 7. So to reiterate, when we're looking for the square root and we want to do the prime factorization method or the method down here, what we're doing is we're actually getting all the prime numbers or the prime factors of 448 or whatever the number under the radicand or that makes the radicand. And you're saying, can I construct two equal groups of the prime factors, and those two equal groups will make a number that's a perfect square. Okay, so now for the second example, we're going to deal with taking an entire radical that's a cube root and making it a mixed radical. So off to the side here, I've written, instead of the squared table or the perfect squared table, I've written the perfect cube table. So now that we have the perfect cube table, the first method that we did, even from the last example, is we said, what was the largest perfect square that divides this number? In this case, we want to say, what's the largest perfect cube that divides this number? In this case, it's actually the same value. So we're going to get is equal to cube root of 64, because 576 divided by 64 is going to give us 64 times 9. Or 576 divided by 64 gives us 9, so then we know 64 times 9 will give us that 576 back. And then what's the perfect cube of 64? Well, perfect cube of 64 is just 4. Based on our table, we just reverse the step, or we move backwards like this, and then we trace it. If we trace back like that, then we know it's going to be 4. So I get cube root of 4 cubed times 9. Yet again, we can separate those. See, we get cubed of 4 cubed times cube root of 9. And if we cube a 4 cubed, that's going to just give us 4. And then we're going to leave our 3, or our cube root of 9, because we can't cube root 9 without having some form of a decimal with that. So that would take our entire radical and convert it into a mixed radical. Now let's show the prime factorization method. We're going to start by taking 576 and divide it by the 64, just as we did in the last problem. That gives us 64 times 9. If we break 9 into its prime factors, that's going to be 3 and 3. If I take 64 and divide it into its prime factors, I'm going to get 8 times 8, then 4 times 2, then 4 times 2 for this 8, 2 times 2 for this 4, and then 2 times 2 for this 4. Now, what did we say about the last problem? We said we wanted equal groups of the prime factors so that they could be squared. In this case, we want, instead of 2 equal groups when we're squaring, we want 3 equal groups of the prime factors. So if I want 3 equal groups of prime factors, I have 6 2s and 2 3s. So I know the 3s can't be involved because a 3 can't be involved in each of the groups. So I know we're just going to be dealing with the 2s. And if I had 6 2s, I can group these 2 together. I can group these 2 together. And then I can finally group these 2 together. That's 3 equal groups of the prime factors available. And yet again, 3 can't be used because when we only have 2 of them, we can't distribute a 3 to each of those groups equally. So now what does my radical become? If I have cube root of 576, I can actually say this is going to be, what's 2 times 2? That's going to be 4. And how many times do I have this group of 4? Or how many times do I have 4? Well, 3 times, because we have 2 times 2 in the green, 2 times 2 in the blue, and 2 times 2 in the red. So we get 4 cubed. And then our remainder, which is going to be these terms here, the 3 times 3. So, and what's 3 times 3? That's just 9. Now the process becomes the exact same. We get cube root of 4 cubed times cube root of 9. A cube root of a cube is just the number itself. And cube of 9, well, that isn't a perfect cube, so we're just going to leave it under the cube root. And there we go. We have the exact same answers. So to reiterate like last problem, what we're going to do is I'm going to say, if I'm doing the prime factorization method, I'm going to want to take this 576 and divide it until all the numbers are prime numbers that make its factors. And then I want to assign the numbers such that they make equal groups to make the numbers. So for this, we had equal groups or 3 equal groups of 2, and we couldn't make equal groups using the 3, so we knew that was our remainder. Quite honestly, you'll end up using this method a lot more. So this first method of picking one of the highest cube roots, or specifically the highest perfect cubes. And then in the last problem, you're going to most likely pick the highest square or perfect square. But knowing the prime factorization method tells you where these numbers specifically come from to make these tables work the way they do.